Hello guys, in this video we are going to see the exercise which can help you to understand the theory about Lewis structure. Please watch my previous video about the theory of this topic because it's useful to understand now the rules that we will apply in this case. So let's start with the first exercise. First exercise is write the Lewis structure of N2. So the molecule of nitrogen, what will be its Lewis structure? We have to remind the rules. First rules was to count the valence electrons of the molecule. So let's follow the first rule. Now the nitrogen has 5 electrons as valence electrons, but since we have 2 nitrogen, we have to multiply this by 2 and the result will be 10. So 10 are the valence electrons, but it's better to divide this 10 by 2 in order to obtain the pairs of electrons instead of electrons. This will help us to deal directly with pairs. So this will be equal to 5. So 5 are the valence pairs of electrons. Now let's write the result here. 5 is valence pairs. Okay? Because this we have to settle in this molecule in order to have the Lewis structure. So we have to use all of them. Otherwise, the structure is not complete. Let's go to our second rule. The second rule was about the central atom. The central atom is the least electronegative atom. So it's about the central atom in the molecule, which is the least electronegative. Now, of course, electronegative cannot be written like this, it's just that I'm using abbreviation, okay, to speed up. Now, what is the central atom in this case? In this case, we don't have central atom because this is a binary molecule, so we don't have that, okay? We can skip that and go to the third rule, which is about bonding, the calculation of bonding electrons. So how many bonds we have in this molecule? We can already write that this molecule will be done by N, okay? Put already one bond, because at least with one bond these two atoms should be linked together. So we are sure of this. How we can calculate the bond electrons? To calculate the bond electrons, we have first to calculate the octet electrons. So what are octet electrons? Octet electrons are the number of electrons related to the octet rule. So we have to ask ourselves the atoms we have in this molecule, which kind of octet rule are following. They are following the octet rule, they are following the incomplete octet rule, they are following the expanded octet rule or the duet rule. So in this case we have nitrogen plus nitrogen. Nitrogen is an element which is following straight the octet rule. So this nitrogen is following the octet rule, also this nitrogen, because they are part of the same element. So which will be the number of octet electrons? Will be equal to 2 times 8. 8 is related to the octet number of electrons, okay? So 2 times 8 is 16. So these are the electrons of the octet. Now we have to divide by 2 to obtain the pairs of octet electrons. So we have 8. How we can calculate the bonding pairs? The bonding pairs can be calculated just by making the difference between this and this. So the bonding pair of electrons are equal to 8 minus 5, which is 3. So this means that we will have 3 bonds in this molecule. One bond we have already settled. So we need to settle other 2 bonds. Where we can write these 2 bonds? We can write them here between these. Again, we don't have other options, so we have to put it here without doubts. So this is a triple bond. Now we have done with the bonds, so we can go to the 4th rule, which is about the lone pair. So the 4th rule is telling us to put the remaining electrons here as a lone pair. So first of all, we have to know how many of these lone pairs we have. This is pretty simple because it's the difference between the valence pairs minus the bonds or the bonding pair, which is 3. So we have to settle these 2 pairs of electrons. Where we can put it? We have to put these 2 pairs of electrons in a manner that each atom will observe the octet rule. So how many electrons we have around this nitrogen? We have 2 electrons coming from each bond, okay? Because the contribution of each bond is 2. So this is 2, this is also 2, and this is also 2. So we have 6 electrons around this nitrogen. This means that this nitrogen needs 2 more electrons to reach the octet. So let's put these 2 electrons, which correspond to one of our lone pair. So this nitrogen now observe the octet rules. Let's see this last nitrogen. This last nitrogen actually is equivalent to this one, because also this one has only 6 electrons now around it. So, as we have done also before, we need another pairs of electrons to reach stability also for this second nitrogen. Stability in this case is of course the observation of the octet rules. Now it's done because we needed to settle only 2 lone pair, and we have done it. One is here and one is here. If you count how many pairs of electrons we have, it will be 1, 2, 3, 4, 5, which is equal to this one. So now we know that everything is fine because we have used all of these, the valence electrons, and everything is fine also because each atom is observing now the octet rule. So this is our Lewis structure. During the video about the theory, I give you also other 2 rules. The 5th rule was about resonance. I told you to watch if there are possible resonance structure. There are possible resonance structure here. Actually, yes, because we have anyway a multiple bond. So what can happen is that this bond will go here. So the result is but the problem is that when I do this, now this nitrogen will be negatively charged and this will be positively charged. This is actually a resonance structure of this. Okay, we can put this double arrow. But the problem is that this resonance structure is not highly stable because we have a separation of charge. All the time we have separation of charge in comparison with neutral molecule. The neutral molecule will be the most stable one. So actually, yeah, it's possible that there is also this resonance structure, but it's not stable. So the 6 rules that also I give to you during the video about the theory was to see the formal charges. But I told you that formal charges is useful to be calculated only when you have multiple structure which are possible structures and you don't know which structure is true, which structure is fake. But in this case we don't have doubt. This is the only structure we have here. So the exercise is actually finished and we can move on and we can now go to the second one. So second exercise is about writing the Lewis structure of OF2. What we have to do is to following again all of these rules. So let's start from the calculation of valence electrons. How many electrons we have here? We have The valence electron of oxygen are 6. The valence electron of fluorine atoms are 7. However, we have 2 fluorines, so we have to multiply this by 2. Then we have to sum up everything. So we will have 7 times 2 is 14. 14 plus 6 is 20. So we have 20 electrons. But we want to work with pairs of electrons because it's easier. So let's divide this by 2. So we will end up with 10 pairs of electrons. The first rule is done. Let's write here how many pairs of electrons we have as valence pairs. Okay. Now, what is the central atom? Okay, in this case, the central atom will be oxygen, because oxygen is less electronegative than fluorine atoms. Actually, fluorine atom is the most electronegative atom in the periodic table, so we don't have doubt that oxygen will be in the middle of this molecule. We can already write at least 2 single bonds, because, as I have already told you, it's sure that there will be at least 2 single bonds. Otherwise, how this molecule can exist. Now, bonding electrons. How we can calculate bonding electrons? Well, we have to repeat what we have done before. So, bonding electrons, first we have to calculate the octet electrons. Okay, so you have to ask yourself which atom is following the octet rules or it's going in the exception. Both oxygen and actually fluorine are following the octet rule. So we can write 8, because oxygen will need 8 electrons around itself and the fluorine the same. So it will be 8 times 3, because in total we have 3 atoms following the octet rule. And this is equal to 24. Divided by 2, we will have 12 octet pairs of electrons. So now the bonds will be equal to these 12 pairs of octet electrons minus 10. So 12 minus 10 is 2. So in this molecule we will have 2 bonds. Let's write it here. But 2 bonds is something we have already written. Now I have to move to the last point, which is the lone pair. Calculation of lone pair. Let's write it as LP to go faster. So lone pair will be equal to the difference between these 2. So it will be 10, the valence pair minus the bonds is 8, because 10 is our total electrons we have to settle around our molecule. 2 are the number of bonds, so what is left is lone pair, okay? That's the reason why we do this difference. So we need to put 8 lone pair in a manner that each atom will follow the octet rules. So let's start from, let's say, oxygen. Oxygen has around it 2 electrons coming from this bond, 2 electrons coming from this bond. So it has already 4 electrons. But to reach the octet, so to reach 8 electrons, this means that we need more electrons, so we need other 4 electrons. So let's write it as lone pair. Here are 2, here are other 2. And now this oxygen actually reaches the octet. Okay? And now we have used 2 of these lone pairs, so we have 6 lone pairs left. So this fluorine has only 2 electrons around it. To reach 8, it will need 6 more. So let's write here. So we have used 6, so we have left 3. This 3 lone pair, of course it's easy, will go on this fluorine atom because it's equivalent to this one. So now it's finished. So let's just see if we can write some resonance structure. So our 5th rule. Actually, there are no resonance structure here because there are even no double bond. And the last point was the 6th point about calculation of formal charges. Since we don't have doubts with other structure, it's pretty useless to calculate these formal charges. So we are already sure this is our right structure. So the exercise is ended. Now we can move on to the third exercise. So third exercise is writing the Lewis structure of ACN. So we have a poison here. We have this highly toxic acid. So how to write this structure? We have again to follow the rules. So actually I will add now even the 5 and 6 rules just to remind us. So resonance structure, and the 6 is formal charges calculation. So now it will be more clear. So ACN, let's start from the valence electrons calculation. Okay, hydrogen has 1 valence electrons, carbon has 4 valence electrons, and nitrogen has 5 valence electrons. Let's sum everything up, and they will have that the total is 10 electrons. Again, let's divide by 2, and we will have 5 pairs of valence electrons. So let's write here 5 valence pair. Let's write it with this abbreviation. Let's go on. Which is the central atom? Okay, the central atom, if we follow strict this rule, should be the least electronegative atom. So should be hydrogen. Okay, let's write this thing. Okay, this thing is not possible. It's not possible because hydrogen cannot do more than 1 bond. Hydrogen is following duet rule, so it cannot have 4 electrons around it. Okay, so this is a mistake. So let's go to the second less electronegative atom, which is actually the carbon. And now it's right to put the carbon here in the center. Okay, I'll write the structure here. C, N, and H. So this rules is true in most of cases, but in some cases, as you can see, for example, this molecule, you have to think a little bit more, okay, because otherwise you will do a mistake. But just think that hydrogen, of course, cannot stay in the middle, never can stay in the middle of the molecule. Now, bonding electrons. How many bonding electrons we have? Okay, bonding electrons can be calculated by, first of all, we have to calculate the octet electrons, which will be given by the total electrons coming from the observation of octet rules. So hydrogen observed the duet rules, so it requires 2 electrons around it. So let's write 2 electrons plus carbon needs 8 electrons, so let's write 8, and nitrogen needs 8 electrons to be stable. So let's sum everything up, and it will be, the total will be 18. 18 divided by 2 is equal to 9 octet pair of electrons, OP. So the bond electrons, the bonding pair of electrons, BP, will be equals to the difference between this and this, which is 9 minus 5 equals 4. So we need 4 bonds. We have 4 bonds in this structure. Now, 2 bonds we have already settled, so there are 2 bonds left here. Where we can put these 2 bonds? I cannot put another bond here because, as I have already said, hydrogen makes only 1 bond. Following the duet rules, hydrogen has already 2 electrons around it, so it won't react more than this. So now we have to put the left bonds here. So there are 2 bonds, and then we write them here. This is also done. We have in total 4 bonds. Let's go to lone pair. How many lone pair I have? It's simple because lone pair if we write here 4 bonds pair, lone pair are equals to the difference between valence pair and bonding pair, which will be equals to 1. So actually I have only one lone pair in this molecule. Where is located this lone pair? This lone pair is located on the nitrogen. Why? Because, as we have already said, hydrogen has already observed the duet rule having 2 electrons here. Carbon also has already observed the octet rule because he has around it 2 plus 2, 4 plus 2, 6 plus 2, 8 electrons. So carbon is now stable. The only thing that hasn't already reached stability is this nitrogen, because this nitrogen has 2 plus 2 plus 2, which is 6 electrons around it. It needs more electrons equals to 2 to reach the octet. 2 electrons equals to 1 lone pair, and so we have done. There are resonance structures. Yeah, it's possible that this double bond is moving here, this multiple bond is moving here, but once you do that, you will have something with separation of charge, because now this will become minus and this will become plus, and this is not stable. So let's say there are no resonance structure. Formal charges, we need to calculate these formal charges? Of course not, because we have only one structure here. We don't have doubts. So also this exercise is finished. So fourth exercise is about the molecule NCO-. Actually is an anion. Again, let's calculate the valence pair of electrons, which are equals to... So how many valence electrons we have for nitrogen is 5 plus... Carbon is 4 electrons. Oxygen is 6 electrons. Let's sum everything and it will be 15, which is odd number because it's not quite... Okay, it's not odd number because we forgot the minus charge, which is another electrons to be considered. Okay, so the total is 16, which is now even number, so we can divide it by 2 and we will have 8 electrons. So 8 are the valence pair of electrons. These are the total pairs we have to place in our molecule. The central atom is the least electronegative atoms, which is carbon. Carbon will be in the center of this molecule. Let's start to write a draft of the structure here. Okay, this is done. Let's move on with the bonding pair of electrons. Bonding pair of electrons can be calculated after the calculation of octet, as usual, electrons, which are equals to, actually this time is 3 times 8, because all of these atoms are following the octet rule. So 8 plus 8 plus 8 equals to 24 electrons, that divided by 2 is 12 pair of electrons. This is octet pairs. If you do the difference between 12 octet pairs of electrons minus 8, we will have that 4 are the number of bonds. So we will have 4 bonding pairs to place here. 4 bonding pairs. 2 we have already put it here, so we need to put other 2, so I can write 1 here and 1 here. I don't know actually how to write now this multiple bond, because I can have also another situation in which the bond will be the 2 remaining bonds. I can put both on between C and O, or I can put both between N and C. So which structure is more stable? We cannot say it now. Of course, if you know that carbon triple bond oxygen is something very weird to write. You can already rule out this one. But for now, let's pretend that we don't know. And let's go on. Let's go on, using all of these three structures. So we are now to write the lone pairs. How many lone pairs we will have? Lone pairs, it's the difference between these two. So 8 minus 4 is 4. So we will have 4 lone pairs in this structure. Okay, we have to write this 4 lone pair here in a way that each atoms will reach the octet. Now, if you observe, each of these carbon has already reached the octet number of electrons, because we will have 2 plus 2 plus 2 plus 2, so which is 8, and also here we will have 2 plus 2 plus 2 plus 2, and here. So we cannot place this lone pair on the carbon. What is left is oxygen and nitrogen. Here this oxygen has 4 electrons around it, so it will need more electrons, equal to 4 electrons. So 2 lone pairs here. Now this oxygen is stable. Nitrogen has also 4 electrons, so it will need 2 pair of lone pair. Now all the lone pair have been placed. Let's do the same for this structure. This oxygen here has 6 electrons around it, so it will need only 1 lone pair. This nitrogen actually has only 2 electrons, so it will need 6 electrons, 3 lone pair. 3 plus 1 is 4, so everything placed. Here it will be the opposite. 3 on the oxygen and 1 on the nitrogen. So which structure is true, which is fake? We can do it now with these 2 last rules. There are resonance structure. Of course there are, because we have multiple bonds. This double bond can be placed here, and this will shift here. What we will have? We will have this one. See, because this lone pair goes here, forming this triple bond. This carbon have to be only 8 electrons. This means that this double bond cannot stay here, because now carbon has 1 more bonds with oxygen, and so this will shift on the nitrogen, giving this. On the other hand, if I move this lone pair here, this has to shift here, and I will gain this structure. So the relationship between these 3 structures is that they are resonance structure. We can write the minus sign outside the brackets. All of them, they can be true. But which one is more true? We can answer to this question by using our 6 rules. So, calculation of formal charges. As I have said to you during my theory video about these 6 rules, there are 2 ways for calculation of formal charges. One is using a formula, which is this one, and another method is visual method, which is my preferred one, so I will use that one. So I take the bonds and I divide each bonds in half. So now the contribution of this bond to each atom is not more 2 electrons, because I have divided, but is 1 electrons for bond. So let's count how many electrons has around itself nitrogen. 2 plus this one is 3, 4, so 4 lone electrons plus 1 coming from this half bond and 1 from this half bond. So it's 2 electrons from this double bond in half. So it's 2 plus 4 is 6 electrons. But nitrogen has a valence electrons, which is equals to 5. So if you 5 minus 6 equals minus 1, so it means that for doing this kind of structure, nitrogen has acquired a negative charge, which is formal charges actually of nitrogen. So let's write minus 1 above our nitrogen. Let's repeat the same for carbon. Carbon has around it 1 electron from this bond, 1 from this, 1 from this, 1 from this. In total is 4 electrons. The valence electron of carbon is 4, so 4 minus 4 is 0. So the formal charge is 0 on this carbon. Now, since the total formal charges should be equal to the charge of the molecule, and since the charge of the molecule is minus 1, this means that this oxygen should be 0, otherwise I cannot have as total charge -1, okay? So you can either repeat the calculation of the formal charge for oxygen, or you can consider the total final charge, which should be on this molecule. Let's do the same here. So I will divide it in 2 halves, this bond. Also, let's do for this. Let's calculate the formal charges. So this is 1 electrons plus 6, it's 7 electrons. The nitrogen valence electrons are 5, 5 minus 7 is -2. So the formal charge is -2. Again, for carbon is 4 electrons around it. 4 is the valence electrons of carbon, so 4 minus 4 is 0. And here it will be 1, 2, 3, 4, 5. 5 electrons around oxygen, but the valence electrons of oxygen is 6. So 6 minus 5 is +1. So this oxygen has a +1 charge on it. Check if everything is fine. The total charge number is -2 plus 0 plus 1, which equals to -1, which corresponds to the charge of our molecule. So it means we have done everything right. If you repeat what we have done here also for this one, you will end up with this charge on nitrogen, which is 0, 0, -1. We can see that this is 0 on oxygen, 0 on carbon, pretty okay, they are non-metals. And there is -1 on nitrogen, which is also non-metals element, pretty okay this structure. This structure has 0 on carbon, which is okay, -2 on nitrogen, yeah, it can be, because nitrogen is anyway non-metals, so. But +1 on oxygen, or cannot be stable, these things, because a minus+ or electronegative oxygen, which is non-metals, which is electronegative elements, make these things not stable. This means we can rule out this one. What about this last structure? This last structure is okay, because -1 is on this non-metals element, so it's okay. So what is the final structure of NaCO anion? Is actually a combination of these two structures that I will rewrite now. Okay, so the right Lewis structure is combination of these two. Of course, we can say that this is probably slightly more stable because the formal charge was -1 on oxygen, which is more electronegative element than nitrogen. It's more likely that the negative charge will end up on the oxygen. In this other case, the negative charge was on nitrogen, which is slightly less electronegative than oxygen. So this is slightly more unstable, this is slightly more stable. That's all, we can move on to the last exercise. Write the formula for this anion, quite famous anion, sulfate. So again, valence bond, valence pair will be equals to 6 coming from the sulfur, 6 coming from the oxygen times 4, because we have 4 oxygen. If you sum everything up, will be equals to 30 electrons. If you divide it by 2, will be 15 valence pair. As usual, let's write the result over here. So it's 15 valence pair. Which is the central atom? The central atom, we don't have doubt, is sulfur, because sulfur is less electronegative than oxygen. So sulfur will go in the center. We can already write 4 bonds, because are the minimal bond we can have in this structure. Let's go to the third rule. Bonding electrons. Bonding pair of electrons will be given by calculation of octet electrons, which will be equals to numbering of electrons from the octet. So oxygen is following the octet rule, so it's 8 electrons times 4 because we have 4 oxygen, plus the contribution that came from sulfur. Now we know that sulfur can either following the octet rule or following the exception of this octet rule, which is the expanded octet with 10 electrons or even 12 electrons around it. So how we can know which kind of octet sulfur will have? We cannot know that. We cannot know that. So we have to try everything. That's the simplest things we can do. So we have to try all the octet. Now let's start from the case in which sulfur is following straight the octet rule. So we have to add another 8 here. So it will be 8 times 5, which equals to 40. 40 divided by 2 is 20. Now the bonding pair will be equals to 20, which are the octet pairs, minus 15 equals 5. Okay, actually we did a mistake here in the calculation of valence pair, because actually the valence pair are 16. Sorry for that. Are 16 because I forgot the negative charge. So if you repeat the calculation of valence electrons, we will have 6 electrons from sulfur plus 6 times 4 from oxygen plus 2 electrons from the negative charge. So everything will be now equals to 32. If you divided this by 2 is 16 valence pair. Never forget, that's an example of never forget the charges in the calculation of valence electrons. So now it will be different here. It will be 20 minus 16, which equals to 4 bonding pair. So we can write it over here, the result. So in the case of sulfur with 8 electrons around it, the bonding pair will be 4, which is something we have already placed here in our first draft, so we don't have to do anything. Now let's calculate the bonding electrons in the case of sulfur with 10 electrons around it, so with the expanded octet. Okay, so the octet pair of electrons will be this time again 8 times 4 coming from the oxygen plus 10 this time coming from the sulfur, because it has extended octet. The result will be 42 divided by 2 is 21. The bonding pair will be the difference between 21 minus 16, which equals to 5 bonding pair. So in the case of sulfur with 10, it will be 5 bonding pair. And if you repeat again this calculation for sulfur with 12 electrons, 2 electrons more, it will be 1 more from here, so it will be 6 bonding pair. So we need to write 2 more structure which are considering the different kind of octet the sulfur has. So this is our sulfur with 8 electrons, this is our sulfur with 10, and this is our sulfur with 12. Okay, in the case of sulfur with 8, we have to place 4 bonding pair and we have it done. In the case of sulfur with 10, we have to place 5 bonding pair. So we have to add 1 more bonding pair here. In the case of sulfur with 12, we have to add 2 more, because we have already 4. 4 plus 2 is 6, so we have to add 2 more. Let's place them here. Now let's move to the fourth rules. So we have to calculate the lone pair for each structure. Okay, the lone pair for this one, it will be given by 16 minus 4, which equals to 12. 12 lone pair. We'll write it under the structure here. Okay, 12 lone pair for this structure. The lone pair will be 16 minus 5 for this one, which equals to 11 lone pair, and 16 minus 6 equals to 10 lone pair. Pretty simple. Okay, so we have to place 12 lone pair here. The sulfur already reached its octet, so we don't have to place lone pair on the sulfur because we have 2 plus 2 plus 2 plus 2, which is actually 8. So sulfur already follows the octet rule. We don't have to bother about sulfur. We have to now consider the oxygen. All of these oxygen have already 2 electrons around them. This means that they need 3 pairs of electrons per each oxygen to reach the octet. And 3, since we have 4 oxygen, 3 times 4 is actually 12 lone pair, so we have finished. And all our molecule will have... Then let's write like this, with 2 minus here, because the final structure has double negative charge. Let's do the same for sulfur with expanded octet to 10 electrons. So sulfur should have, now be careful, because sulfur is following the expanded octet rule, so around it needs not 8 electrons but needs 10 electrons. So let's count everything. It's 2 plus 2 plus 2 plus 2 plus 2, which is actually 10. It's already 10, so we do not have to use our lone pair for the sulfur. This oxygen has only single bond, so it means it has around it only 2 electrons. So to reach the octet, it will need 6 electrons, which equals to 3 lone pair. The same for this oxygen, because it's equivalent to the first one and also this one. So how many lone pair we have placed it? We have placed it 3 times 3, which is 9. So the difference is 11 minus 9 is 2. So we need to put 2 electrons on the last oxygen. Let's verify if this oxygen has 8 electrons. So 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. So yeah, it's done also for this one. Now, if you repeat the same from this one, the same exercise, you will end up with this situation I write now here. Okay, just try by yourself. Take into account that this sulfur should have 12 electrons around it, and do the exercise by yourself. So this is our situation. We have 3 structures. There are resonance structure here, 0.5. Okay, here we do not have resonance structure because we have just single bonds. Then here it's likely that you will have resonance structure because this bond, I can write in this position, this double bond, but also I can write this double bond here, or here, or here. I will have 4 resonance structure. And also here I can write in a different way these 2 bonds. So it's sure that we will have resonance structure for these 2 ones. But now it's not urgent to see resonance structure. So because we need to establish which of these 3, so with the sulfur with 8, sulfur with 10, or sulfur with 12 electrons is more stable. So let's skip this one for now. And let's go directly to the 6th one about formal charges. And we need to calculate formal charge for all of them. So I'm using this visual, as we have already said, method to calculate the formal charges. If you don't like it, use the formula. I give it to you during my theory video. So the formal charge for this sulfur will be 1 electron for this half bonding pair, 1 from this, 1 from this, so it's 4. This sulfur has 4 electrons around it. But the valence electrons of sulfur is 6. So 6 minus 4 means that during the formation of this structure, the sulfur acquires a +2 charge. This is its formal charge, so let's write it here. Let's repeat the same for oxygen. This oxygen has 1, 2, 3, 4, 6 and 7 electrons around it, but the valence electron of oxygen is 6, so 6 minus 7 is -1. So -1. These are equivalent to oxygen because all of them have 3 lone pair and 1 bonding pair, so they will have the same charge. We do not have to repeat the same things, okay? It's stupid. So let's calculate the total formal charges. Will be minus plus minus plus minus, it's -4. -4 plus -2 is -2. So actually is in accordance with the ion, the charge of the ion. So we have done it correctly. Let's repeat the same formal charge calculation for this one. Sulfur has now, after the division of the bond, has around it 1, 2, 3, 4, 5 electrons. But valence electrons for sulfur is 6, so 6 minus 5 is plus 1. So this is formal charges. The formal charges for oxygen with one bond, this situation is equal to this situation, so we don't have to repeat it. It's minus 1 for the oxygen with one bond, so this minus. Okay, the formal charge for this oxygen, we have to calculate it. So we have here 1, 2, 3, 4, 5, 6 electrons around this oxygen. The valence electron of oxygen is 6, so 6 minus 6 is 0, so this is 0. Let's verify if everything is okay by the calculation of total formal charges. So plus 1 and minus 1 gives 0. Minus 1 and minus 1 gives minus 2, which is in accordance with the charge of the ion. So everything is okay. Okay, do this by yourself. I will write directly the solution here. So which structure is true? Okay, this structure has plus 2 sulfur. So plus 2 sulfur on non-metals elements is something very unstable. So we can erase this one. This one, again, plus 1 on sulfur. There is something better. Let's see. Yeah, this one. This one which has 0 on sulfur, which is fine for non-metals element. This is with sulfur involving expanded octet with 12 electrons is our true structure. These ones are not stable, we cannot keep them. So our final structure is this one. So we have the 5 rules we have skipped before. So now let's be back to that. There are possible resonance structure. I told you already that yes, there are possible because this structure is actually equivalent to this one. Moving this double bond here in horizontal. Of course, put the right lone pair. You have to keep lone pair in a clever way. So move also the lone pair. And then also it's possible this one with one in vertical and one in horizontal. And it's not finished because we have also this other possibility. Okay, so we have 4 possible resonance structure. So now it's everything for this last exercise I wanted to show you. If you want to follow me on Patreon, we will do more exercise. In particular, we will do exercise with radical molecule, which can be important for your examination. So if you want to follow me there, please check the link below.